Welcome to the first of a series of videos introducing the CodePeer static analysis tool developed by AdaCore. So first of all, what is CodePeer? It's a static analysis tool. It's not your average static analysis tool. It's a very advanced static analysis tool which is designed to determine what could happen when the program that you've written or the piece of a program that you've written actually runs. What kinds of failures, what kinds of assertions will it violate, and fundamentally it will give you the kind of feedback you would normally get through executing tests. It will give it to you during the early phases of development. CodePeer is not a tool designed to identify coding standard violations and so on, but it is packaged with a tool called gnat check, which does that kind of analysis to be sure that you're indenting your code according to your coding standards, that you aren't using features that you're not supposed to use, and so on. CodePeer itself is all about trying to find problems that would normally show up only at runtime. And by doing mathematical analysis, CodePeer is able to determine what sorts of problems might occur at runtime. Another aspect of CodePeer is because of its in-depth analysis of the program, it can also generate what we would call as-built documentation, so that if you are going to be doing code review and you're concerned perhaps that the comments that are currently in the code may not necessarily reflect the actual code that's been produced, CodePeer can extract, if you will, from the program documentation that is pretty much guaranteed to be a faithful representation of what the code actually does. Information such as what global variables does this particular function reference? Are there any limitations in terms of what values as inputs might cause the subprogram to abort and so on? Anyway, we'll give you some examples of all of these. The key point is that you can execute CodePeer early in the life cycle and still find problems that normally you wouldn't find until you were able to actually execute tests. It's designed to be modular and scalable to large projects. You can start by running it on any individual compilable file, grow up to analyzing libraries of modules, and ultimately up to an entire program or a set of programs. It can be designed to be very strict, or it can be focusing just on the most serious problems. And you have pretty much total control over the kinds of messages that CodePeer will highlight. You can also run CodePeer multiple times on code that is evolving and use it to compare any earlier run of CodePeer against your most recent run. It handles essentially all versions of Ada, starting from the original 883 up to the most recent 2012 version of Ada. It supports some of the newest features of Ada 2012, including those having to do with user-written pre- and post conditions. You'll see that CodePeer also infers implicit pre- and post conditions, and these two work together very nicely. It's based on the gnat compiler, but it's designed to analyze code that is currently being compiled with other Ada compilers, such as Apex or Green Hills or Object Ada, or even the older Vertex Ada design system. As mentioned, it does include tools that can be used for doing coding standard checking and so on, as well as tools for doing conventional metrics analysis, such as cyclomatic complexity and so on. So when you purchase CodePeer, you get not only this advanced static analysis tool that's focused on runtime issues, but you also get other static analysis tools that are helpful for doing conformance with standards and with developing metrics if you have limits on certain metrics, or you just want to keep track of what is the metrics associated with individual tools. So emphasizing the reason why it's useful, that CodePeer is finding problems early in the life cycle, and I think all of us have this awareness that the later you find a problem, the more expensive it is to fix, especially if you've actually deployed a program to customers or within your own organization. Having to deal with problems at that stage is much more expensive. CodePeer can really be used as soon as you have your first compilable component, even if you can't have something that could actually execute it. It may be just a single subprogram, or it may be a small library. CodePeer can be used right away. So how does CodePeer work? One of the interesting things about CodePeer is it works what we would call bottom-up, sort of like a compiler. It doesn't need a complete program to do useful analysis. it can take an individual subprogram that it can compile and analyze that and try to figure out, well, what sorts of inputs might cause trouble. So it doesn't actually require caller test harnesses to check out the logic of a subprogram. It can look just at the subprogram itself and analyze where it might go wrong. And how does it do this? It does this by computing the possible value of every variable and every expression that occurs within the subprogram. It determines what possible values would be at each point in the subprogram. And then it says, well, could that value cause a problem? For example, if it's a pointer, might that pointer be null when you dereference it? Or if it's used as an array index, might it be out of bounds of the array in which you're indexing? To be more specific, here are some of the runtime issues that CodePeer checks for in every function and procedure that it looks at. Remember that it's already determined possible values of every variable and expression within your program. This allows it to see whether if you use an index value, it's outside of the array, or if you divide by a value or an expression, that expression might be 0. Other checks, tag check, which has to do with object-oriented programming. Discriminant check has to do with when you have variant records and you might be referencing the wrong variant. Access check is just another word for a null pointer check. Range and overflow check has to do with numeric calculations to be sure that they don't go outside the range of the declared Ada subtype of your variable, or in the case of an overflow check, outside the physical bounds of the numeric type that you're using. And finally, validity check is really just another name for a check to be sure that all of your data is correctly initialized, that is, it has a valid value. It's also possible for the user to effectively create their own checks in Ada. You can write a pragma assert pretty much anywhere, and it will check to be sure that that assertion is true, and if not, it will raise an exception, such as the assertion error. You can also just write code using explicit exceptions. So you could say if x is greater than 10,000, then raise some exception. Or you could raise an exception in a place where you believe it should never reach. Essentially, you're claiming that this code is unreachable. A user precondition is something that's a new feature of Ada 2012, and CodePeer will see if you've written any preconditions. That is, you've specified, I want every caller to satisfy the following precondition before the call to the subprogram begins. CodePeer will go and verify that, in fact, that precondition is in fact satisfied. Similarly, a postcondition is a claim that the result of the subprogram that you called will satisfy the following postcondition. And again, CodePeer will make an attempt to prove that that postcondition will always be true after executing the subprogram. So these are ways that you can add additional checks, which CodePeer will in fact attempt to check to see if they're in fact satisfied by the code that you're looking at. Another set of checks that CodePeer does for you have to do with race conditions. That is, when you have multiple threads of control in your program, multiple Ada tasks, and they're referencing variables. Two tasks might be referencing the same variable. The question is whether they are properly synchronizing their access to those shared variables. You don't want two tasks where one is writing and one is reading at the same instant of some object. That would be a race condition or a data race, a particular kind of race condition, and CodePeer looks for situations where that might occur. Finally, there's a check that is associated with CodePeer's ability to infer preconditions. That is, CodePeer is able to look at a subprogram and say, well, it looks fine, except that if you give it an input that's, let's say, negative or greater than 100,000, there's a chance the subprogram will fail some internal check. And rather than blaming that on this subprogram, we're going to really say that the caller should not send in those sorts of bad values. And we will propagate that precondition to every call site and verify that at every call site it satisfies those requirements. And we'll keep propagating it until we get to a point where, in fact, it's violated. For example, perhaps you read a number from some input device and then immediately pass it down the chain. That's where the mistake is. Right there when you read it in, you should have performed probably some kind of a validation check and you didn't. So one of the nice things about this capability is that CodePeer will identify the root cause of a problem, saying that really the bad data came into the program here, even though the actual runtime check might be significantly further down in the program. Finally, in addition to checks, CodePeer also produces what we call warnings. Warnings are for code that looks suspicious or maybe doesn't seem to do anything. For example, if you have a piece of code that can't be reached, let's suppose you say if x is greater than 100,000, then do something. And CodePeer can pretty easily prove to itself that x will never be greater than 100,000. Then that code is useless, can't be reached, and in some certification standards, that would be a problem for you to even certify your program because you've got unreachable code. Similarly, that test, if x is greater than 100,000, the test is always false. And that is, again, a situation where you could run into trouble trying to certify the program. Furthermore, it's also going to make it very hard to do full coverage analysis of your program if you're trying to be sure that every statement is executed. Furthermore, if you just have individual expressions within a more complicated one that are always true or always false, individual Boolean expressions, if you have if x is greater than y or z is less than 3, and in fact x is always greater than y, that's another case where you might want to know that you've got a condition that always returns the same value. You could also have a loop whose exit condition is never true, so you think it's going to go until such and such is true, but in fact CodePeer can convince itself that that will never happen. Obviously you'd like to know about that. The next 4 of these have to do with different kinds of assignments that look suspicious. You assign a value into some variable, and then you immediately assign a different value to that variable. That first assignment is unused. Or you might assign to a global inside some subprogram, then when you come back, no one looks at the value of that global, so that's sort of a waste. Similarly, you might assign into an out parameter, and then none of your callers look at it, so it's not very interesting. And finally, there's a case where you compute some new value for a variable, and that new value CodePeer can prove to itself is always equal to its old value, so that new computation is not accomplishing anything. Other kinds of warnings have to do with other sorts of suspicious situations. CodePeer has the ability to infer preconditions. As mentioned, this is used in various ways to propagate checks to callers. But if those preconditions have a gap, that's a little bit strange. For example, if the precondition says that this input must be in the range 0 up to 100,000, except that 305 is not allowed. Well, that's a little strange. Why not 305? Well, maybe it was a situation where you had multiple modes of computation, where if the values are less than 305, you did one algorithm. If they're greater than 305, you did another. And if it's equal to 305, you didn't actually say what should be done. So it, in fact, raises an exception of some sort. Another situation, the next 2, is where you have an out parameter that you read or an in-out parameter that you don't read. So clearly you have the wrong mode. Or you have an in-out or an out parameter that you never write. Again, that sounds like you have the wrong mode or the parameter just isn't of interest. Finally, you have a situation where you do some complicated computation and it always produces the same value. Probably means you're doing a divide by a number that's too big and you didn't recognize that you were doing integer truncating divide as opposed to some kind of more precise floating point divide. Many of the issues identified by CodePeer's checks and warnings correspond to vulnerabilities that are included within MITRE's Common Weakness Enumeration, otherwise known as CWE. CWE has become more and more important these days, and it's mentioned in many government contracts and in various cybersecurity requirements. CWE is an enumeration of all of the common vulnerabilities that appear in software applications, and CodePeer has been certified to be compatible with CWE in the sense that when it finds a problem that corresponds to a CWE issue, it will provide you with that information as a CWE identifier. Furthermore, if you have a particular CWE identifier you're looking for or interested in, you can do a search to see if that particular error is showing up in the current application being analyzed. We also provide a mapping more generally between CodePeer findings and CWE identifiers in our documentation. And we encourage you to look at the CWE feature of CodePeer.